Focus करना ठीक है Focus भी ठीक है Reach Reach Focus नहीं कर पाएगा
இல்லை இல்லை வெயிட் தெரியுதா
ಇಲ್ಲ ಸರ್ 3 minutes ರೆಡಿ ಆಯ್ತು ರೆಡಿ ಆಯ್ತು
Distinguished dignitaries, respected faculty members, esteemed speakers, researchers, scholars, excellence. It is truly inspiring to see such enthusiastic participation both offline and online.
Behind the first session of day 2, it is my pleasure to invite our respected Dr. H. Hannah Inbarani ma'am to kindly invite our honorable chief guest for today's program.
So good morning to all the online and offline participants. You all for session 3 of International Conference on AI and Smart Computing Techniques. Now I would like to introduce the resource person of this session, Kumar Pisaradi. It's my great pleasure to introduce our esteemed speakers, including major multi-center funded initiatives. A recipient of prestigious Charles Zuckerberg Initiative Imaging Scientist Award, he continues to push the boundaries of precision diagnostics and translational neuroimaging. Ladies and gentlemen, please join me in warmly welcoming Dr. Pramod Kumar Pisaradi. Now we look forward to your insightful and inspiring address, sir. Welcome you, sir. So over to the resource person, Dr. Pramod Kumar Pisaradi, sir.
Sir, please, sir, kindly share your screen.
Hello, can you hear me? Can you hear me okay?
Yes, sir.
Okay.
So your voice is not audible, sir. It's not clear, sir.
It is not clear?
Now it's clear, sir.
Okay, so shall I just try sharing my screen once?
Yes, sir. Yes, sir.
Okay, let me share this. Okay, so can you see my screen now?
Yes, yes, sir.
Okay. Okay, so I will start sharing and then. Okay.
Slideshow, sir. Full screen mode.
Yeah. Right from start. Is that okay?
Yes, sir. Yes, sir. Now it's okay.
Okay. So do you want to keep it like this, or I can stop it and then maybe I can share it again after we start?
Yes, sir. We can start now.
Okay. Okay, go ahead. Oh, sorry. I want to. Okay. So let me know when you are ready to start. Okay.
Professor, please share your screen, sir.
Yeah, I already tested, but is it like, are you waiting for some more people to join or? I cannot see anyone, so.
So already several people have joined, sir. There are several offline participants and online participants. Are you able
Okay.
to view offline participants, sir?
Okay, so are we starting now?
Yes, sir. Yes, sir.
Okay, yeah, I'm all ready. So, yeah.
Okay, okay. We'll wait, sir. Wait.
Yeah.
Sir, we can start now.
Okay.
Yes, sir. Yes, sir. Are
So
you
I can
able to
start.
view? Yes, sir. Offline. Are you able to view the offline participants?
Okay, so I was waiting to see if there is an introduction or anything, but you're asking me to start right away, right?
Yes, sir.
Okay, yeah, we'll start. Yeah, it's already, I think, 10 minutes past, right? Yeah, so first of all, I want to thank all the organizers of this conference and Madam Dr. Hannah Imperani for inviting me to deliver a keynote talk in this conference. Yeah, thank you for the invitation. And yeah, like I was asking Madam to share yesterday's program link. I watched the program link, the inaugural ceremony yesterday, in which the opening speech Madam was referring to Dr. APJ Abdul Kalam's quote on achieving excellence. So like many of you, I'm also a fan of Dr. APJ Abdul Kalam, and he is my role model too. And let us start today's session remembering him, more importantly, his words in achieving research excellence. Let us start this session with a pledge for striving for excellence in not just in AI, but in research in general. So I have given plenty of time, almost 1 hour and 15 minutes for this talk. I also noted that there are many students attending this talk, so I have included some slides about my research career, which may be useful for some of the students. I will start with that, and then we'll move on to the technical part of this talk. Okay, I started my career in, basically I'm from Kerala. I did my BTech in Instrumentation and Control Engineering at NSS College of Engineering, Palakkad. So that is under the Calicut University. So here is a beautiful image of the hill view of my college. And after passing out from NSS College in 2003, I worked a few years in NTPC Limited as well as Center for Development of Advanced Computing, SEDAC, Thiruvananthapuram. Then I moved to Singapore, National University of Singapore, for my PhD in Electrical and Computer Engineering. That shows an image of my graduation ceremony. So at NUS, my research was focused on computer vision and machine learning. Specifically, I addressed the complex background problem in congestion recognition using a Bayesian model of visual attention. And after that, I worked in Singapore for a couple of years as a research scientist in the Singapore government's research agency. And I also want to mention that doing PhD in Singapore is a good option for students in India in general, because Singapore invests lots of money in research, and they do have some attractive research scholarships. So if any of the students interested, you can Google for graduate admission in National University of Singapore. So you Google for NUS graduate admission, and you will find useful links about getting scholarship for doing PhD in Singapore. And there are also a couple of other very good universities in Singapore. One of them is called Nanyang Technological University, and another is Singapore University of Technology and Design. So in general, like, I mean, when I was trying for my PhD options in US, that was not really affordable at that time, but I found Singapore got very good scholarships. Yeah, so you can take a look if you are interested. And then I moved to MIT, Massachusetts Institute of Technology, for my postdoctoral research. As some of you know, MIT is a very good place for engineering research, especially for artificial intelligence. So that image is me standing in front of MIT back in 2014. And the image on the right side is called Computer Science and Artificial Intelligence Laboratory, which is like the best place for research in AI. I was not in CSI, but in the biological engineering department, my research was in biomedical imaging. I will talk about that in a while. Specifically, I started my research in diffusion MRI analysis and some mathematical modeling, at MIT. And then, again, for if you are interested in postdoctoral research, I think you will learn more about that when you do a PhD, but there are many conferences in this field, and these professors advertise postdoctoral opportunities through the conference web pages. So that is how I found this opportunity and ended up at MIT for my postdoctoral research. And then I moved to University of Minnesota. I was in the Department of Radiology here. Right now, I hold a joint appointment between the departments of neurology and radiology. We do have 5 campuses. I'm at the Twin Cities campus. So these are 2 neighboring cities, Minneapolis and St. Paul. I'm in the Minneapolis campus. And what I'm showing here is a nice summer view of our campus. Right now it is winter time here. Right now the outside temperature is like less than 0 degrees centigrade, which is considered a mild winter because we used to have -30, -40 degrees centigrade in severe weather conditions. Yeah, so at Minnesota, yeah, like the university itself is established in 1851. Uh, the nearest city that you may be familiar is Chicago. We are about like 400 miles northwest of Chicago. Like the other universities I attended, University of Minnesota is also one of the top universities, and my research here is mainly focused on MRI-based biomarker development. We'll talk a lot about that uh, in my subsequent slides. So that is, yeah, yeah, one slide about the center where I'm working. So this is in the University of Minnesota Medical School. The center is called the Center for Magnetic Resonance Research. So it's basically high field MRI research. An image of our center on the left, and on the right, I'm showing like a 10.5 Tesla human MRI machine. So we do have 10 MRI machines, 7 human machines, and 3 animal machines. So basically, the strength of the MRI machine, the magnetic field strength, is specified using Tesla. We do have 3 Tesla, 4 Tesla, 7 Tesla, and 10.5 Tesla, which is considered the world's like the machine we had is the first highest magnetic field strength machine for human scans. Right now, there are other machines, but ours was the first in the world. So that is all about my background. So now we will move to the technical part of this talk. Can somebody please confirm everything is okay at your end? I hope you can listen to me all good.
Yes, sir, it is okay, sir. We are able to view our screen.
Okay, all good, right? Okay. So, yeah, I will start with detailing the human brain imaging method we are working on. In general, MRI, specifically a method called diffusion MRI. So that is measuring water diffusion in the brain using high magnetic field for imaging structural connections in the brain. And then I will explain the computational modeling that we have done to analyze the diffusion MRI images, because diffusion MRI images are not directly interpretable by a neurologist. So some computational modeling is needed. Especially, I understand the focus of this conference is on computing. So I hope that will be relevant to attendees of this conference. And then once we have this imaging and computational modeling done, we need to apply these methods to the clinic. So how we can use it in hospitals. So then I will talk about what is called a translational neuroimaging, how we can translate these methods to clinic, specifically application in neurological disorders like ALS, amyotrophic lateral sclerosis, as well as Parkinson's disease. Okay, I got some confirmations. Yes, all good. That's good. Okay, thank you. So basically, I will explain how we improved sensitivity of diffusion MRI to disease-related structural changes in these neurological disorders. And towards the end of the talk, I will discuss some of our ongoing research, which is deep learning-based super resolution in MRI. And I will talk about some of the multimodal methods. So how we are improving MRI resolution using microscopy. Sorry. Okay, human brain. So what I'm showing here is an image of the human brain. So as you can see, the brain is connected to the spinal cord, and the spinal cord got number of distributions going to all the muscles of the human body. So basically, we analyzed both the brain as well as the spinal cord. We segmented the spinal cord into different fiber tracts. Basically, there are like ascending and descending tracts. So the tracts which are ascending from the brain, which control the muscles, and then the tracts which are ascending to the brain. Descending are the motor tracts, and ascending to the brain, which are basically the sensory tracts. So the human brain is considered the most complex object in the known universe. Our brain consumes more than 20% of the body's total energy, despite making up only about 2% of total body mass. So that is the complexity of the brain. Human brain is complex, especially because there are more than 86 billion neurons in the human brain, forming trillions of complex neural connections. And if we extend all the neuronal connections, the total length of neurons in the human brain will be about 850k kilometers. So you can assume how complex those connections are. So even if we open the brain, we cannot really see those axons because those are basically at like nano or micro scales. But the good news is that we have some good imaging methods, specifically the magnetic resonance imaging method, which is very useful in human brain imaging. So MRI is a very safe medical imaging modality compared to other modalities such as X-ray and CT scan. And it uses high field magnets such as 3 Tesla, 7 Tesla, and 10.5 Tesla. And I also want to mention that MRI is a Nobel Prize. MRI was discovered much earlier than 2003. The Nobel Prize was awarded in 2003 to Paul Lauterbach and Sir Peter Mansfield for their discoveries concerning magnetic resonance imaging. So here is a comparison of conventional MRI and diffusion MRI. So the conventional MRI is also called structural MRI. The contrast is called T1, T2, or FLIR contrast. So what I am showing here on the left is a FLIR image of a brain tumor. So that is from our project on tuberous sclerosis complex. So all the highlighted high intensity areas here are the tumors in the brain. So we analyze the same brain using diffusion MRI, and you can see that diffusion MRI is giving much more detailed picture. Basically, diffusion MRI can provide the neuronal fiber connections. So the brain should be symmetrical. The healthy brain should be symmetrical on both sides. So you can see here that the right side, there are some abnormal connections compared to the left side. Similarly, in this highlighted region, there are some abnormal connections. I'm getting some chat here. Okay, so I think that is not for me probably. I hope everything is good at your end, but in case if there are issues, please stop me because I'm talking to the computer. I'm not able to see you. Okay, so yeah, as you can see, the highlighted regions, just compare those with the other side. You can see there are some abnormal connections that we can detect with the diffusion MRI. So a little bit more details about how diffusion MRI works. So there are two types of diffusion in the brain. Those are called isotropic diffusion and anisotropic diffusion. Isotropic diffusion is nothing but random diffusion. So water diffuses randomly in spaces like the ventricles or the gray matter of the brain or the corticospinal fluid. And in anisotropic diffusion, which happens in the neurons. So here I'm showing a diagram of the neuron. So neurons got these long axons. So the water diffuses through these axons. The key idea is that water diffuses only along the axons, but not across the axons. So that type of diffusion is called anisotropic diffusion. Just think about water flowing in a tube. So that diffusion got some directionality, and that particular feature is used in diffusion MRI to image the axonal trajectories. So why we are interested in measuring the water diffusion in the brain? So here I'm not showing the brain, but the image of a night traffic. So here it is night and we really cannot see the road, but we can estimate the road, or we can track the road by tracking the headlights or tail lamps of the vehicles running on the road. Likewise, in brain, as I said, even if we are opening the brain, we cannot really see the axons. But we know that water is diffusing through the axons, and if we can image those water diffusion, basically we can image the axonal trajectories. So what I am showing here is called the tracking of corticospinal tract, which basically connect the top of our brain, basically an area called the motor cortex, through all the way through the neck to the spinal cord. So this particular tract, especially like we tracked this in ALS and we found degenerations in the corticospinal tract. I will talk about that in the later part of this talk, but this is the key idea. Measure the water diffusion in the brain, image the water diffusion in the brain, and using that, develop some beautiful pictures tracking the axons in the human brain. Even more beautiful picture here. Here the colors has some meaning. The red color represents left to right fiber connection. The blue color represents bottom to top, and the green is across the plane. So what I'm showing is a coronal view of the brain, basically a cross section of the brain. And as you can see, it is symmetrical on both sides. So processing of the diffusion MRI can give fiber trajectories like this, which are very useful in analyzing pathological disease data. Another video showing the wiring diagram of the human brain that we extracted. So here you can see the cortical foldings. All these gray regions are the gray matter, the cortical foldings, and you can see the white matter connections on the other side. Actually, it is symmetrical, but only one side is shown here. So we can get some complex wiring diagrams like this using computational modeling of the diffusion MRI data. This also provides wiring diagram of the spinal cord. So basically the brain is connected through the spinal cord. The tracks are connected through the spinal cord, and then there are this area is called cervical spinal cord, and then thoracic spinal cord, and then lumbar spinal cord. So all these areas, the fibers are getting dispersed through the spinal cord to the muscles, and using diffusion MRI, we can track all these fiber connections. So that is basically an introduction to the diffusion MRI. So now I will talk about computational modeling in diffusion MRI. So how we can how we can extract those beautiful wiring diagrams using computational modeling. Specifically, I'm going to talk about a method called sparse Bayesian learning. We use this algorithm for compressive sensing, basically to reduce the scan time in diffusion MRI. So an MRI scanner is shown here, and diffusion MRI data is shown here. So there are a number of diffusion operations. This is all the data. So there are a number of data sets. So each set is magnetic field area. So total acquisition time is about 40 minutes. Like we are to reduce the scan time by 70%, meaning we can get data in about 10 minutes. So this image on the bottom showing the some reconstructions. Those are showing the fiber orientations extracted from the full data, 50% data, and 25% data. So you can see that these are very comparable. So even with 25% of the data, we can get very high fidelity, high quality reconstructions, which is very useful in reducing the scan time, basically the time the patient need to be spent on the scanner. So we used our algorithm is named BISINX, Bayesian unmixing for sparse inference-based estimation of crossings. I will talk about that a little bit more detail in the next slides. So basically, we formulated this parameter estimation problem as a sparse inference problem. Basically, we want to estimate the neuronal, the axonal fiber directions as well as the volume fractions of the fibers. So there are crossing fibers which we named as fiber 1, fiber 2, and fiber 3. So we modeled this data using what is called a dictionary formulation. I guess some of you may be familiar with that. So we represent the data using a dictionary, and once it is formulated as a dictionary, we used a model called ball and stick. Basically, the stick represents the axons and the ball represents the isotropic diffusion components. So once it is represented in a dictionary, the problem boils down to estimating the dictionary weights, which are this particular vector shown here, which are basically the fiber volume fractions. So once we estimate the fiber volume fractions, we get the corresponding orientations, and that solve the problem of estimating the fiber orientations. Little bit mathematics here, more details about the sparse Bayesian learning. I don't think I will explain that in very detailed, but basically we used a hierarchical Bayesian network that got many hyperparameters controlling the variance of a Gaussian distribution that we used as a prior. So even though we used a Gaussian distribution for the prior, once we do the posterior estimation using the Bayesian estimation, all the parameters are integrated out, and after integrating out the hyperparameters, this Gaussian distribution will turn to a student T distribution. So you can see that the probability density is high at the origin where all the weights are 0, and also along the spikes where one of the weight is 0 in this case. So in our case, it is n-dimensional, but many of those weights are pushed towards to 0. So in other words, we are enforcing sparsity. And the deleted weights are those for which the noise explain the data better. So in that way, by enforcing sparsity, we do what is called a relevance learning. So more relevant or more accurate fiber orientations are automatically selected. So moving on to some results, as I said, like we did estimations with the full data, meaning no undersampling, that is like 40-minute acquisition versus 20-minute acquisition versus 10-minute acquisition with 75% undersampling. That means only 25% of the data is used. So this is a region from the centrum semi-ovale in the brain, and we got very high fidelity estimations even with a 10-minute scan. So this is useful in reducing the scan time, the MRI scan time. The data I was showing, this one was there was some limitation. We needed 2 acquisitions of the data, but we have extended that to single resolution, single acquisition as well. As we are comparing here, if you look at this yellow arrow, you can see that our method estimated with less uncertainty. This shows like more uncertainty in the other method, and also more number of fiber crossing, more number of fibers as compared to other methods. Like the crossing fiber is detected compared to another method which didn't do the detection of the crossing fiber. So this is like 2 fiber tracks going like this, which is detected better in our BISINX method. And we also compared the number of crossing fibers detected and found our method is detected more number of crossing fibers. So I'm moving to the next part. Maybe I can break the talk for a while if there are any questions. I don't know, like I'm seeing anything here. I don't think so, but feel free to unmute and ask any question, or if you want me to proceed, that is fine too. Okay, I didn't hear anything, so I hope I can continue. So we will move to the translational neuroimaging and application to neurological disorders, specific. Hello. Can you hear me?
Hello.
Hello.
Sir, hello. Sir, what is ARD, sir? Automatic relevance determination.
Can you please provide me some feedback? I would like to listen.
Sir, hello. Audible my voice?
டைப் பண்ணிடலாம். டைப் பண்ணிடலாம்.
Yes, sir. We are hearing you.
Can you hear me okay?
Yes, sir. Yes, sir. Now, okay, sir.
I'm sorry. I don't know. Like, I mean, are you able to listen? I need some feedback, please.
So, what is automatic relevance determination? A or B?
Okay, I really cannot hear you, but can you type in the chat whether everything is okay, because somebody.
Chat bar will come to the chat box, will come to typing from your query.
So what is automatic relevance?
Automatic relevance determination, A or B.
Oh, okay, that was a question. Okay. So what is automatic relevance determination? So basically that is called, it is called like, I mean, giving some regularization for the weights so that the orientations that are relevant will pop up. So we did that using what is called a relevance vector machine. So that is basically determining the orientations that are relevant, that support the data automatically. Does that answer the question? Okay, so I do have some issues in listening to you, but I hope I can just continue.
Sir, here so many diffusion MRI techniques are used. 5, 6, 7 or 10.5. Minnesota or USA or highly 10.5 MRI machine is available from human scan. So you know what type of indexing to identify this brain, especially brain in neuron cell.
Okay, I will continue. Okay, I hope this is still visible. Okay, so words are very good. Okay, very good. Thank you. So, so we applied these methods to amyotrophic lateral sclerosis, which is a motor neuron disease. So as you can see on this left image, the brain is connected through upper motor neuron to the spinal cord, and from the spinal cord to the muscles using what is called lower motor neuron. So in ALS, there is a degeneration in this upper motor neuron and lower motor neuron. There are more questions coming, but maybe I will continue and I can take that at the end. So basically this voluntary muscle movements are affected when there is degeneration in this upper motor neuron and lower motor neuron, and most of the people die due to respiratory failure within 3 to 5 years of the first symptom. So it is a very fatal disorder. So we imaged the spinal cord as well as the brain of these patients. We imaged the cervical spinal cord, the areas from C2 to C7, and we did segmentation of the spinal cord. Basically, the ascending tracts to the brain as well as the descending tracts from the brain, and we segmented the white matter and gray matter, and within the white matter all the ascending and descending tracts. These are some of the fiber tracts that we segmented, and we found that when we do the segmentation of the spinal cord tracts, the sensitivity of the method is improved. So the method here used is called the varying coefficient model. So basically the diffusion property is connected with the covariates of interest using what is called the varying coefficients. So here the covariate of interest, I have shown an example here, like the disease status and the connection to age, and then any scan of dependence. So the varying coefficient we are interested here is the coefficient corresponding to the ALS status. Ideally, for healthy participants, that should be 0, but if there is some significant difference due to the disease, it will be non-zero. So as you can see, so this varying coefficient is in this case deviating significantly from 0, showing some disease effect. So using this varying coefficient model, we found some significant differences along the spinal cord, which we plotted here. So look at this left top image where the whole cord, meaning like the spinal cord without any segmentations, analyzed. As you can see, like this blue color here represent the healthy control data, and the red color shows the ALS data. You can see that there is some clear difference between these two participants along the spinal cord from C2 to C6, and that gap is increasing with segmentation, meaning like in these two pictures you can see the gap is even more. So when we segmented the spinal cord, basically the sensitivity of this method improved, which is reflected here in a p-value heat map. So this shows the p-value heat map. So red means statistically significant and blue means not significant. So you can see that when we move from left to right, this is becoming highly significant. We also found which are the specific tracts affected in this disease, like the lateral CST as well as the spinal lemniscus. And we also, okay, more chats coming, but yeah, I hope I can continue. So we also analyzed the whole cord cross-sectional area, basically the cross-sectional area of the spinal cord, and we found highly significant difference between these two groups, control and ALS. And basically this means that sensitivity of the spinal cord MRI to this disease is improved. And what I have shown in the previous slide is the comparison between patients and healthy participants. And what I am showing here is basically the longitudinal change over 1 year. So we collected the data both at the baseline as well as after 1 year. I know that this graph is a little bit busy, but it shows the variations in multiple diffusion features along multiple fiber tracks. I invite your attention to these two graphs here where I have shown some increase in this diffusion metrics, what called mean diffusivity and radial diffusivity over 1 year. So this basically measures the disease progression, and this is especially useful in testing medications. So if we want to know whether a medication is working or not, we can use this method. Correlation between these imaging metrics and some clinical measures. You know, this neurologist got some functional measures. So when we go to a hospital, they do some test, and then they calculate some functional measures. In this case, it is called ALS Functional Rating Scale Revised. So we found some strong correlations between imaging metrics on this x-axis and then the functional measures on the y-axis, both in the cervical cord, diffusion measures, as well as the cross-sectional area. Not just the spinal cord measures, but we analyzed the brain measures as well, and we found many areas affected, disease-related changes in many areas of the brain. As you can see, this like a red color here shows highly significant p-values comparing the healthy participants and patients. More importantly, we combined the spinal cord data with brain data, what is called a multimodal MRI, and then we found that can improve the disease detection accuracy. We did this study in 20 ALS and 20 control participants. We combined the data from brain and spinal cord, and even within the brain and spinal cord, we combined the diffusion features with morphology features, meaning the thickness of the cortex, as well as the cross-sectional area of the spinal cord. And then we used a multivariable logistic regression. And then I invite your attention to this last row here, in which you can see that we got 87.5% diagnostic accuracy and 90% sensitivity and 85% specificity, better compared to the single modality methods. More importantly, a specific class of ALS called missing, the ALS in which the UMN upper motor neuron signs are missing, which is very difficult to diagnose in the clinic. In this case, we got very high diagnostic accuracy when we used multimodal MRI. MRI can detect longitudinal changes in the brain as well, and it can detect changes in 6 months. So we use some measures called fiber density, fiber cross-section, and fiber density and cross-section. And we found that we can detect these changes in 12 months as well as in 6 months, which is very important in clinical trials of medications. So right now I'm leading a multi-center MRI study in ALS with the University of Florida and Northwestern University, in which we are demonstrating the clinical trial readiness of our method. So I'm moving on to the Parkinson's disease. I don't think we have much time left, so only a couple of slides. What I want to say here is that we found very highly significant degeneration or changes in Parkinson's disease as well. So the left image compares Parkinson's disease patients with healthy controls, and we found statistically significant increase in fractional anisotropy in these participants. More importantly, we compared two specific subcategories in Parkinson's disease. So those are called RSWA, REM sleep without atonia and with atonia. So those are some complex definitions, but take it as Parkinson's disease patients with and without sleep issues. So we found there are some statistically significant difference between these groups. So the group without the sleep issues, in that group, there is some neurocompensatory changes happening. So in other words, they have less severe disease because there are some neurocompensatory changes happening in the brain. So if we can understand what is going on in that, that also will be helpful in developing medications. We are not there yet, but we had this preliminary findings on the Parkinson's disease progression. I'm moving to the last part of this talk. I think we have about 10 more minutes left. So this is about our ongoing research in which we are using deep learning for creating super resolution in MRI. So basically we are combining MRI with microscopy. Sorry. So what I am showing here, these are different imaging contrast from a method called PSOCT. PSOCT stands for polarization sensitive optical coherence tomography. It is a tomography method. It is basically a microscopy method which can image brain of the order of micron resolutions. So this is postmortem data. This is postmortem monkey brain, in which we acquired both MRI as well as PSOCT data. So the images shown on the left are the PSOCT contrast, and the rightmost column is MRI. And this image here also MRI. So basically an area highlighted here shown, it's a small ROI. As you can see, the resolution of the MRI is, it is an in vivo method. It is pretty good, but compared to the microscopy got much higher resolution. So different contrasts like cross polarization, retardance, reflectivity shown here together with the fiber orientations. So the color coding here shows the multiple fiber orientations. Another image comparing PSOCT and MRI. On the right, MRI is shown, the whole brain imaging. The other one was only an ROI. And here you can see that again, PSOCT got higher resolution, even in orientations. So we can learn a mapping between MRI and PSOCT using deep learning, and then we can apply that to in vivo data for improving the MRI resolution. So this is an ongoing research. What I'm showing is very preliminary results. So how we did that? We used ESR GAN. So that is an enhanced super resolution generative adversarial network. As you may be knowing, GAN is a new type of deep learning method. And we achieved 8x resolution improvement in the MRI using the ESR GAN. So what we did is we did a transfer learning of a network, ESR GAN network trained in computer vision. We did that because we have limited data, MRI data, but in computer vision, abundance of data is available. So we used a network that is already trained on computer vision and did transfer learning to get the desired results. So here is a link to the preprint that we are working on now. And the input is, as I said, MRI with lower resolution, and the ground truth is PSOCT. For example, we used 27 by 20 pixel size voxel in MRI because it is 3D. And then the ground truth is what I am showing here, which is more than 100x resolution higher. So with the limited data, we could not bridge that big gap, more than 100x resolution gap. But what we did is we did a super resolution by a factor of 8x. So that is what I am showing here. So this is an ROI from the brain shown here. So original MRI shown on the left, and enhanced resolution MRI shown in this middle column, and then the PSOCT images are shown on the rightmost column. So multiple slices are shown, and as you can see, there is significant improvement in this small ROI, which we are trying to apply to the whole brain now. And we are exploring more advanced model like the diffusion models, implicit diffusion models. That is something we are working on right now. So I'm moving to my concluding remarks. Diffusion MRI is useful in portraying neuronal connections in the brain as well as the spinal cord. It is not directly interpretable, but advanced computational modeling is required, and it is very useful to get all the neuronal fiber connections in the brain. And diffusion MRI has potential use in early disease diagnosis and assessment of disease progression. And lastly, the future is with AI for improving MRI resolution, as I briefly demonstrated. And also, I envision in future there will be more like smart MRI scanners that can do even pre-diagnosis or diagnosis of the disease using some of these methods. I want to acknowledge the help I received from many of the colleagues and team members, and also to the many funding agencies funded our research, and also to all the patients, their families, and healthy controls who participated in this research. Thank you again for inviting me to this conference. And I'm sorry for the interruption in between. It seems like there is some issue in the voice. I could not hear you well, but I assume I was audible and everything is good. And let me know how do you want to proceed with the Q&A and interaction. Okay, I have stopped sharing, and I think I have, let me go through the questions. Okay, automatic relevance determination, I think we talked about that. Which mathematical model are more suitable for sparse Bayesian learning? So I don't think there is any specific mathematical model that is in favor of the sparse Bayesian learning, because the model we used is called ball and stick. But yes, there are many other models available. Yeah, I don't think the model itself is sensitive to the sparse Bayesian learning. It is based on like how you want to formulate the parameter estimation problem. Yeah, so the model will affect that, but sparse Bayesian learning should work for any of these models. Okay, yeah, I think the web page shared there was not very updated, mouthkp.com, but I think you can of course follow my Google Scholar profile and my profile at UMN. Which model performed best for ALS prediction, and how did you validate its generalization ability across different patient populations? Okay, that's a big question. So the answer to that is we really didn't do prediction in ALS. So the work what I presented is measuring progression. So these two are different things. So that is called progression biomarker and prognostic biomarker. So the progression biomarker will measure the disease progression, versus prognostic biomarker will predict progression. So what we did is progression biomarker, because our purpose is to use this in clinical trial of medications. So we want to know whether the medication is working or not. So it is not prediction, but assess or measure the longitudinal change. But yes, if we are using deep learning for prediction, then of course we have to validate it on independent cohort. But yes, I have reported some diagnostic accuracy for which we did some cross-validation and fault cross-validation. Yeah, I hope that answers that question. And how does the reduction in cervical cord CSA correlate with disease severity or progression rate in patients? Okay, that's a good question. So basically, these are neurodegenerative progressive diseases. So when the disease progress, there is thinning of the the cortex as well as neuronal degeneration. And when there is neuronal degeneration, the spinal cord cross-sectional area will come down. So that represents the neuronal degeneration with the disease progression, which is reflected in lesser cross-sectional area of the spinal cord. Okay, is there any other questions? How are graph theory models used in neuroimaging? Yeah, graph theory is used a lot in neuroimaging. That is basically used in brain network analysis. So even graph neural networks are used. So basically, like what I have shown is the neuronal connections and fiber tracks, but we can extract the brain networks using these methods, and then we can apply graph theory for brain network analysis. Why is advanced computational modeling necessary for interpreting DMRI data, and how might AI-based MRI resolution enhancement and smart MRI scanners improve its future applications? Okay, so there are two parts. First is how is like computational modeling, why computational modeling necessary? I think I have explained that, because it is not like the diffusion MRI contrast. If a neurologist is looking at that, he or she will not be able to interpret anything. So computational modeling or those neuronal parameter estimations needed to make the interpretations from diffusion MRI. And then the second part is how might AI-based resolution enhancement? Yeah. So like any resolution enhancement, say in computer vision, we get more finer details with resolution enhancement. So that is applicable here in MRI as well. So with resolution enhancement, we will be able to see more fine details or more fine neuronal connections. Okay, what are supervised and unsupervised learning methods in neuroimaging? Okay, so I don't think there is big difference in neuroimaging between these two methods. So as you may be knowing, there are like methods like clustering and all, or self-supervised learning, which are unsupervised, and then everything else in which we do training is supervised. The method I was talking about is supervised. So we do have a training and validation and testing phase separately. But otherwise, there is no difference in neuroimaging. But one thing I can tell is like in neuroimaging, the data is limited. It's not like computer vision. We don't have millions of images because we need to acquire this data from patients. So the availability of the data is limited. So that is why we are using some strategies like the transfer learning. So I think that is all the questions. Naveen got another question just typed in. Let me read that. Can computational neuroimaging predict neurological diseases before symptoms appear? Okay. Very good question. So, okay. So I would say we have not reached there yet, because so say what I was talking about is about ALS or Parkinson's. So in these cases, like we kind of know that these patients are already diagnosed. But if we want to do an MRI scan of a healthy participant, healthy subject, and predict the possibility for not just for ALS or Parkinson's, but Alzheimer's or frontotemporal dementia or any other disorders, much more work needed. So for that, we need larger data sets, and we need to use AI and do more training. But I'm sure that we'll be there in maybe another 10 years. Say, for example, here in United States, these things can be included in a routine annual wellness visit. An MRI scan can be included, and we can potentially predict the probabilities of these disorders. We are in nascent stages of that, but maybe another few years, I think we'll be there. I think that is pretty much about all the questions, and I think we are almost at our time limit. Okay, maybe one more question. How can computational neuroimaging improve next generation brain computer interfaces? Okay, good. So in brain computer interface, if we want to do brain computer interface, we should know what is going on in the brain, or like how to interface or where to interface. Or even for these treatments, there are like there is a method called deep brain stimulation, which is a treatment method in Parkinson's disease. So in this task, we should know where to stimulate or what to do in the brain. So for that, we need to know even more about brain, and that is the role of computational neuroimaging. So definitely developments in computational neuroimaging will enhance brain-computer interface methods. Okay, I think I will stop it there. Thank you again for hosting me at this conference, and for all these excellent questions. Irrespective of this voice issue we had, I hope we were still in good shape. Yeah, thank you.